Hello, class. This PowerPoint is going to cover engine operation, specifically gasoline engine operation. Okay, we're going to talk about the function and the operation and how the overall engine works. Okay, so what's the purpose of the engine? Why do we have an engine? So a couple things. I'm going to bring all three bullet points, sorry, 4 bullet points up to this screen here. Couple things. The engine itself converts heat chemical heat into mechanical energy or mechanical movement. Okay. Now, that chemical that is converted is gasoline itself. So, gasoline is burned, then we're taking that energy from the gasoline that's being burned and we're turning it into mechanical energy so the engine can propel the vehicle. Okay. Obviously, if we want some sort of creature comforts, kind of like air conditioning and power steering, older power steering systems did use the engine to create pressure for the power steering pump. So those items would be operated by the engine as well. So air conditioning, power steering, and the alternator on our traditional vehicles. Okay, these are traditional gas-powered vehicles, no hybrid systems, nothing like that. Um, then the last thing relates to the alternator. So the alternator charges the battery as the vehicle is moving. Otherwise, the battery would go dead. So the engine is what turns the alternator to charge the battery. Okay. So again, we are taking gasoline, we're burning it, which we're changing it into heat and into pressure, which we'll explain more in a minute. And we're turning that into a mechanical movement. And that's what actually gets our engine to propel the vehicle down the road. Okay. Now, again, these are just basic concepts. We're starting very, very basic in this PowerPoint. Okay. So, combustion. What is the idea on or definition of combustion? So, combustion is, again, we're taking this chemical, which is gasoline in this instance, and we're converting it into a heat energy and specifically at a controlled rate, as it says here. So we're controlling it. It means we're not just letting it explode in the atmosphere or in some bucket or something. But what they mean by controlled is that it is within the combustion chamber. So now the combustion chamber is where the piston comes up, and we create a very small space between the bottom of the cylinder head and the bottom of the valves and the piston coming up from the bottom. And that's where our controlled combustion is taking place. Okay, once we see some pictures in a minute, it'll make a little more sense. Now, that's where we get the word or the term internal combustion engine, ICE, and that's what that's what engines are called. You know, the technical name for them, so to say, is an internal combustion engine. Because again, we're creating combustion, which means we are igniting fuel within a confined, controlled space. Okay, so we're taking that gasoline and converting it into heat and pressure, which then converts into a linear mechanical motion into the piston, connecting rod, and crankshaft of the actual engine. Okay. So now let's just talk about a couple of the parts before we come back to some of the more technical things. Now there's some parts here. Now the part in the middle, okay, is the crankshaft. The part on the right are our pistons and then our connecting rods. And then on the left over here, the left side of the screen, that is when we put them all together. When we put them all together, that's when we get a rotating assembly. So we take the crankshaft, we take the pistons, connect them to the connecting rods, and the connecting rods connect to the crankshaft, and then we get this rotating assembly. Okay. The combustion is actually taking place on top of the pistons. So the combustion is never felt or seen by the crankshaft or by the connecting rod. That the connecting rod connects the two together. So the piston is where the combustion is taking place on top of the piston. It's pushing the piston down through the connecting rod and into the crankshaft and then rotates the crankshaft. That's how we get that rotating motion to be able to power the vehicle. Okay, a couple things down here. That's what we're talking about when we talk about converts linear motion from the pistons, because again, the pistons are pushing down through the connecting rod into the crankshaft, which then rotates. And each stroke of the engine, which we'll talk about the 4 strokes in a second, each stroke takes about 180 degrees or takes 180 degrees to complete. Now, the two terms here, TDC and BDC, top dead center and bottom dead center, meaning when the piston is all the way at the very, very topmost point, that is top dead center. And then when the piston is the very bottommost point, that is bottom dead center. Okay. As we take those four parts, the crankshaft, the pistons, and the connecting rods, and we put them in what's called the block, okay, the engine block. The engine block, usually made of either iron or aluminum or sometimes steel. Um, this is, the foundation of the engine. This is where we put everything into the engine and then we connect everything to the engine. So it's a big piece of metal. It's a heavy piece of metal, and this is where we put all the components into, which is the engine block. Okay, when we put the crankshaft, connecting rods, and pistons into the block, it then can be called a short block if we want to get into terminology a little bit. Okay. Now, like I said, the block is the foundation. So this is a V-type engine that we're looking at here. I can tell because there's 4 cylinders on this side, and then there's 4 cylinders on the other side. So this is a 90-degree V engine that we're currently looking at, okay? And again, the block is the foundation of the engine. That's what kind of holds everything together. It's the body of the engine, so to say. Okay, so we have an engine block, we have the crankshaft, we have the pistons, and we have the connecting rods. Kind of mentioned these 4 parts already, but that doesn't complete everything. Then once we have these parts all together, we have to attach what's called the cylinder heads. So the cylinder heads go on top of the block, on top of the pistons, so to say. Okay. Also, there's a couple other parts that I'm going to show here. These are valve covers. There's different variations of valve covers on newer engines. These are old style valve covers on an old style, like say a Chevy 350 V8 or something like that. Um, and then we have our oil pan. Okay, and then that's on the bottom. That would go on the bottom of the block to hold the oil um, as it's being used, and then when it's not, when the engine turns off too as well. Okay, we put all these things together, and when we get all these components together, the block, the crankshaft, the pistons, the rods, the oil pan, and then the cylinder heads and the valve covers, we put all that together, and then we get what's called a long block. So people can order long blocks. If you go to a parts store, if you go to a dealership, you can actually order a long block to replace an engine that's gone bad. Okay. They do sell long block. Long blocks don't include the intake manifold, basically, is what it doesn't come with, and it doesn't come with any of the accessories. But it comes with all the core components that you would need on an engine to work. Okay. Now let's get into the cylinder heads a little bit. I'm going to bring these pictures up here. The cylinder heads are very important because that's where they contain the valves, and this is where the combustion also happens. So the combustion happens on top of the pistons and under the cylinder heads at the bottom of the cylinder head where the valves are. Now, this picture over here on the upper left, we're looking at, the valves are all removed from this cylinder head, and as you can tell, there are 4 valves per cylinder. This is at least for a 4-cylinder, if not an 8-cylinder engine. You can't tell because we're not exactly sure. We haven't seen the block, but minimum 4 cylinders, and there's 4 valves per cylinder. Okay. If we come over here, this picture on the right, this is looking at the top of an engine. So on the top of an engine, this is a dual overhead cam engine, DOHC. On the top of a dual overhead cam engine, we have the camshafts that rotate and they spin into the top of the valves to open the valves. The springs are what close the valves. Okay. The holes in the center would be where the spark plugs would be. If we come down to this bottom left picture, this bottom left picture shows the valves that have all been removed and then the 4 valves per cylinder. Now, I'm not sure if you can tell by this picture, but if you look closely, you'll notice that one set of the valves is bigger than the other set of the valves. And if we come over to this picture on the bottom right, we have one big valve and we have one smaller valve. I'm not going to say little valve because it's not little, but smaller than the other one. And then we also have a hole here. That hole is for the spark plug. You might notice that there's threads in here. So this is where the spark plug would go. And then we have a bigger valve and a smaller valve. Same thing over here on the left, where we can see the valves lined up here. We have the bigger valves and we have the smaller valves. Now, the bigger valves are for the intake valves. The smaller valves are for the exhaust valves. And this is true of all vehicles. Doesn't matter the year, make, or model. Doesn't matter the manufacturer. All intake valves are bigger than exhaust valves. Okay, because we want to get more air into the engine than it's more important to get more air in than to get the air out. We want to get the air out, obviously, and that's why they're not small. They're just not as important, not as big as the intake valve, because the intake is very, very important. Okay, now let's get to the four-stroke cycle. So the four-stroke cycle on a gasoline engine, and this is also true of a diesel engine, are intake, compression, power, and exhaust. Okay, now a four-stroke cycle takes 720 degrees to complete the cycle. Okay, so the intake stroke is 180 degrees, the compression stroke is 180, the power stroke is 180, and the exhaust stroke is 180. You add those together, or you times 180 by 4, and you will get 720 degrees. That's how we get the 720 degrees, and this is what's called a four-stroke cycle. Okay, and they go in that order too. I'm going to show a picture next. So here's a picture showing the four strokes. The first one on the left, we see that the intake valve is open and the piston is going downward. Now, coming in would be air and fuel. Now, the three things that we would need to make fire, so we're talking about fire, would be a fuel source, an ignition source, and oxygen. So if we wanted to light up a match, right? We need the fuel. We need a piece of wood. We would need oxygen in the air, and we would need some sort of spark, so to say, right? Um, so if we wanted to make fire, we need those three things. Engines require those three things, but they also require one other thing, which is compression. Okay, so we need a sparks. We need a fuel source, which is gasoline. We need an air source, which is the outside air, the oxygen within the atmosphere. And then we need a spark, which is the spark plug. That's our ignition source. And then we need also compression. We need to squeeze this air fuel mixture before we ignite it. Okay. So what's happening in this first one, the first stroke, the intake valve is opening. As the intake valve is opening, air and fuel are being allowed into the combustion chamber. So this is the combustion chamber where this light blue area is with the arrows coming in. Okay. Intake valve open, air is coming in, and then fuel is coming in along with it. So we have air and fuel. So those are two. There's our ignition source, our oxygen and our fuel source. Okay. Then the piston is coming downward in the downward motion. So this is 180 degrees on our first stroke on the left here for our intake. Let's move to the second one where the pink is. Okay. So now the piston is actually coming back up. The air and the fuel are already within the combustion chamber. They're already there because they've been let in by the intake stroke. As the piston is moving upward, you notice that the intake and the exhaust valves are closed now. So now that both valves are closed, the piston is coming upward. And it's going to come up right about to that line right under, that's where the cylinder head and the block meet. So the piston is going to come up to right about that line there. And this is where we are compressing things. So we're actually squeezing the air fuel mixture that's within the combustion chamber. Okay. This is very important because we got to squeeze it all together. Now I'm going to move to the third one because at the third one, this is a little deceiving because on the first one, we're going downward. On the second one, we're going upward. On the third one, we're going downward again. However, the picture is showing that the spark plug is igniting the air fuel mixture as the piston is coming downward. It's actually slightly incorrect because when we are accelerating in the engine, we're trying to build RPM in the engine, the spark plug will actually spark just before we hit TDC, which is top dead center. So meaning the spark plug actually sparks on the compression stroke at the very, very end of it though, at the very end of the compression stroke. And then and it can carry on and carry over into the power stroke as the piston's starting to go down. Okay. Because even though we're showing ignition here in stroke number 3, this burn where the spark plug is igniting the air fuel mixture takes time. It doesn't happen instantly. It takes a few degrees of rotation, meaning we can spark it at about, say, 20 degrees before the piston reaches the top, and then it'll continue on and take place all the way through where the piston's already hit at the top at TDC and then starts to go downward, and then the full burn will take effect right around that point as the piston is going down about maybe 5 degrees or 10 degrees as it's going downward on stroke 3. So the spark is actually starting on stroke number 2 and finishing on stroke number 3. Okay, and stroke number 3 is the power stroke. You notice both the intake and the exhaust valve are closed again, and the piston is going downward. Okay, so we have 180 degrees on intake, we have 180 degrees on compression, then we have 180 degrees on power. And this is what makes your engine turn, the power stroke, stroke number 3. This is what is giving you the power to move the vehicle and to power all of our accessories. Once we have our combustion complete, then we will have the last stroke, which is our stroke number 4, and that is called the exhaust stroke. And this exhaust stroke is going upward. This is our last 180 degrees, and this is pushing anything that's left over is pushing us out into the exhaust system. You'll notice that the exhaust valve is open at this time. So exhaust valve is open. This is pushing anything that's left over, pushing it out through the exhaust system. Then the process starts all over. So again, intake, compression, power, exhaust. 180 degrees for each stroke. 180 times 4 will give us 720 degrees for the 4-stroke cycle. Okay, this is just another quick review of some of the components that are involved in the system. The head gasket is the only thing that I didn't mention. I'm going to go back one slide just to show where the head gasket would be. The head gasket would be right where the piston comes up to this line here. I'm using stroke number 2 as an example. There's a line here that separates the block and the cylinder head. The head gasket would be right between that area. Okay. There's a video here that I would encourage you to watch. I think I do have it on Canvas. If you can get to Canvas and watch that video, there you can shut off the audio. I'm just really worried about the pictures for you guys to see in the video to see the operation. Okay, I'll let you do that on your own time. Some of these pictures are more just for visuals, so you guys can see and look at how some of the components work together and try and visualize things and see how things are working. Okay. Now, there's a couple different types of engine block designs. All right. The one that I think is very common is the inline engine. So inline, meaning all the cylinders or pistons are in a row, like this block shows up here in the upper left. So they're all in a row following each other. All 4 cylinders in production vehicles are 4-cylinder inline engines. Then over here on the right side, you have a V engine. So V, meaning 4 cylinders go to the left and 4 cylinders go to the right. Most V engines are about 90 degrees, but they do make some that are 60 degrees apart, meaning 90 degrees. If you turn some of the cylinders on the side and ran them flat, the other ones would go straight up and down. So the V is 90 degrees long. Okay, and 90 degrees in how do you say in an angle. Okay, sometimes they make 60-degree engines, and then Volkswagen makes a 15-degree engine, the VR6. Okay, where the cylinders are very close together. Um, and then the bottom center one here, this is really only used by 2 manufacturers, Subaru and Porsche. These are boxer engines. So boxer engines meaning 3 or 4 cylinders go left and 3 or 4 cylinders go right, and they are completely flat. Okay, the good thing about these engines is there's a very low center of gravity. But they're the only manufacturers that really use these types of engines. So Subaru and Porsche use these engines. I'm going to skip ahead a little bit here. So this goes over just a little bit more terminology. We talked about inline engines, single overhead cam engines, dual overhead cam engines. So the main difference is the camshafts that open the valves. They are on some engines, they have 1 per cylinder head, or they'll have 2 per cylinder head. So single overhead cam has 1, dual overhead cam has 2. Most modern engines are dual overhead camshafts, meaning they have 2 camshafts per cylinder head. Okay, a lot of this stuff is covered way more in depth in the engine repair class. Okay, this is really meant for our just as an introduction to engines. Okay, and again, this is just another picture of a horizontally opposed or a flat engine or a pancake engine or a boxer engine. Those are all different names to call the same type of engine. Okay. Engines can be mounted either longitudinally or transversely, meaning the engine is either faced front to back along with the car or the vehicle, meaning the front of the car where the bumper is and the radiator is where the front of the engine, and then the back of the engine is where the transmission is, um, right under the vehicle. The other way is to flip it sideways. So we can flip some engines sideways. A lot of front wheel drive vehicles are like, say, like a Toyota Camry or a Honda Civic or a Honda Accord. Those are all front wheel drive vehicles, meaning the engine is in there sideways. So the front of the engine is actually on the side of the vehicle, not in the front of the vehicle. Okay. Just a couple different ways. There's different benefits and drawbacks to both styles. So a little bit on cylinder head designs. So down here in the bottom left, we have a dual overhead camshaft engine, meaning there's two camshafts per cylinder head. One camshaft will open the intake valves and the other camshaft will open the exhaust valves. If we go up here to the upper left engine, we have a V engine, and that's only one camshaft per cylinder head. Even though there's two camshafts total within the engine, there's only one camshaft per cylinder head. Now, the one camshaft will open both the intake and the exhaust valves. Okay. What closes all the exhaust valves are the springs. So all the valves, they have springs in them that will close them. You can see them here. They're real small, but you might be able to see them here in this picture in the upper left. Then the other style is the old school style, so to say. The style that a lot of Chevy engines still use. The Hemi V8 still uses this style. As far as I know, I think Ford has moved away from the style, but they might still have it in their 7.3 Godzilla engine. Um, but they have a camshaft in the block. So they only have one camshaft that's within the center of the block. And that's this picture up here to the upper right. One camshaft center block, and it opens the valves through a push rod design with a rocker arm. So the rocker arms are on top of the cylinder head. The push rod comes through the bottom and kind of articulates and pushes the valve downward. Okay, it's only one camshaft for the entire engine. It's very, very common on V8 engines, older style V8 engines from Chevy and Mopar and from Ford. Okay. And then here are the acronyms for them. So make sure you know these acronyms. They help out a lot. Okay. And this is just another picture of a dual overhead camshaft engine. Okay. There's a little bit here about the rotary engine. I don't want to discuss too much about the rotary engine. It's better if you just see a video of it, because the only manufacturer that did use a rotary engine, and I'm not even 100% sure if they still do, is Mazda. They had the rotary engine in their RX-7s and RX-8s. It used this triangular type of piston design. Usually had I think there's two rotors per engine, maybe three rotors per engine. Some of the race cars, I think, had up to four, but usually just do on a normal production vehicle about two rotors per engine. And it's still considered an internal combustion engine because it still uses gas, it still uses spark plugs, still has a four-stroke cycle, but there is a power stroke every rotation is what happens in these. Okay. If you want more, these are not, again, because these are not common in automotive today, we don't spend a whole lot of time talking about them, but there are plenty of videos online that you can look up and to see how they work. Okay. There's actually one right here. I'm not going to play it on this PowerPoint, but you're welcome to look one up and find a video on it. Okay. A couple things about how affects an engine. So altitude. As you go up in elevation, the density of the air reduces or decreases. Okay. So right here at sea level, so if we live at sea level, you have a higher density of oxygen than you would if you went to the mountains. Okay. And this affects engines because engines need oxygen to work. They need oxygen to ignite the air fuel mixture to create that combustion within the engine. And if we don't have enough oxygen, we're not going to have enough combustion. We're not going to have enough oxygen to feed the fuel to be able to make a burn, a good burn, to be able to increase power. So if you ever drive your vehicle into the mountains, you may notice that you're going to be the engine or the car or the vehicle will feel less powerful, like it has less power, because it does, because there's not as much oxygen in higher altitudes. Now, one way to get around this, or to help with this, I should say, is to use forced induction. So forced induction is turbocharging and supercharging, because we're taking a compressor and we're compressing the oxygen that is within the air, and we're forcing it into the engine at a more dense rate, so to say. Okay. So here's some definitions. Make sure you know these definitions. Go over them. The bore is the inside diameter of the cylinder. The stroke is the distance the piston travels within the cylinder from TDC to BDC. And then I've already explained TDC and BDC. The only ones I haven't discussed are displacement and firing order, but I will discuss that shortly. Now, the stroke of the piston is the TDC to BDC, meaning the piston will go all the way down and then go all the way up. This will relate to and translate to displacement. So how big is the engine, right? If you've ever seen an engine, your engine on your vehicle may be so many liters. It might be a 2 liter engine or 3 liter engine or 4 liter or 5.7 liters or 6.2 liters. So the liters relate to how much volume is within the engine, how much displacement is within in the engine. And that means we're adding all the cylinders up. So if you have a 4-cylinder engine and you have 2 liters of displacement, that means that each cylinder can produce, is producing about 0.5 liters of displacement, because we had to add them up to a 4, up to the number of cylinders you have. And the example I used was 4. So if you have a V8 engine and you have an 8-liter engine and it's a V8, then each cylinder is producing 1 liter of displacement of volume. Okay, so that's how we get to the liters, or the sizes of the engines, the displacement of the engines. Compression ratio has to do with how much distance and how much volume is actually squeezed within the engine. So using this example here, this is an 8-to-1 compression ratio. So the second number is always going to be 1. The first number is the number that changes, meaning we have 8 times. This is squeezing the area within the cylinder 8 times, is what it's saying. Some engines, most engines are around about 10-to-1, maybe like 9.5-to-1. Some newer high performance engines are upwards of 11-to-1, maybe 11, maybe slightly over 11-to-1. Race car engines are like the 13-to-1, maybe up to 14-to-1. And then diesel engines are much higher than that. Diesels can get into the 20s to 1, 21-to-1 compression ratios, meaning they are compressing the volume within the cylinder 21 times. Or they're compressing in a gasoline engine the volume within the cylinder 10 times, which is a lot. That's a good amount. So again, from BDC to TDC, how much are we compressing it? How many times are we compressing that volume within the cylinder? Again, most engines nowadays are around 10-to-1 compression ratio, give or take a couple points. Okay, and the last couple things, what is the definition of horsepower? The definition of horsepower is the rate of doing work. So how much work can your engine do? Horsepower is related to really how quick your engine can be, how much power it can produce, how related to like your top speed, so to say. There's a lot of variations, because just because you have a powerful engine doesn't mean that you can go fast, because there's also gearing involved, the transmission is involved, the differentials involved, the weight of the vehicles involved. Um, how thick, how big, how wide your tires are. That helps too with traction. So there's way more involved than just how much horsepower your engine makes, right? But a lot of people just like to talk about the power ratings of their engines. So the definition is the rate of doing work for horsepower. When we come to torque now, torque is our twisting force. So torque is a twisting force. Torque is like how much how much power you can produce, so to say, by like spinning, by moving, by twisting. Okay. Torque is really, really related to how much you can tow. So trucks have a lot of torque. Trucks will have way more torque than a car, just based on the design of the engine, based on what their needs, right? If you have a lot of torque in a car, that's great. That'll get you going really quickly, but it doesn't really relate to top speed, so to say. Most vehicles with a lot of torque have a lot of lower end gearing within the transmission and or differential too, which creates even more torque because then we're using mechanical gears to create torque as well. And torque is really meant, you really want a lot of torque if you are going to tow something. If you have a truck, you're going to tow. You want more horsepower if you have a car, and because the cars weigh less, you don't need a whole lot more torque compared to a truck. And you want more horsepower in a car than you would in a truck, so to say. Okay, but they do go hand in hand. They work together to be able to create power in an engine. Okay, and then the last thing we're going to talk about is revolutions per minute. So RPM is just the revolutions per minute, meaning how many revolutions is your engine, your crankshaft, spinning within 1 minute. So most engines, they idle at about 750, 800 RPM. As you move through the RPM range, you gain more power. A lot of engines peak at around their peak power rating is around between, say, around 5,000 to 6,000 RPM. That's when you get your peak horsepower. Some engines can go higher than that. As they go higher, though, they will hit a limit, which is the red line, and the computer will stop them from going too far. Okay. Some individuals or some people have taken the red line off. Race cars don't have red lines. They can go all the way up until they blow the engine up until there is a limit. And the limit is when the engine stops working, basically. But all of our vehicles are now computer controlled, so we will limit the computer will limit that to whatever is safe for the engine to operate. Okay, but most cars idle around 750, 800 RPM, right around there, and then most high most engines produce their max horsepower and max torque around between 4 to 6,000 RPM, somewhere in that range. Really depends on the engine. Okay, and the last thing is what displays the instrument? Just answer this question here. What instrument displays the RPMs? And that's the tachometer. Okay, so this picture that we see here is the tachometer. And that is it for this PowerPoint. So hopefully you enjoyed it, and we'll see you guys in the next one. Thanks a lot.